Hello, we're going to talk section 1.7 today, and that's about shifts of graphs. And a shift is when you just take a graph and you do something to it and you move it around, do something algebraically to it. So we want to understand how to shift the graph of a parent function rigidly, and that's going to be up or down, left or right, without changing it. And one way is to do it horizontally, left or right, side to side. They mean the same thing. And what you do there is you take y equal f of x, you take your x, and then you either add or subtract c to it, where c is greater than or equal to 0. And to move it up or down, what you do is you take f of x, and then you add c to it, c to the function. Notice that when I do this here, I take x and then add or subtract c before applying it to the function. Here, I do it after. Now, the other kinds of shifts are non-rigid, and that's when we shrink or stretch. And what you do here is you either multiply the function on the outside by a number greater than or equal to 0, or you take x, multiply it, and then apply the function. And there's two special ones. One is when you multiply by -1, and one is, you take x, apply it to the function, and then multiply by -1. And the other one is when you take x, multiply it by -1, and then apply the function. When you do the first, you reflect it across the x-axis, and a reflect here just means to flip, and you don't change it really, you just flip it. And then, so when you multiply by -1, you just flip across the x-axis. We'll talk about why. And when you take x and multiply it by -1 and then apply the function, it reflects the graph across the y-axis. So we'll start with several examples. And I want to shift f of x squared up by 2 units. And so what I do is it's pretty simple. I'm just going to add 2 to it. So notice that when I add 2 to y, I'm going to be increasing the height by 2. So that means I just shift it up. Notice too that I'm calling the function, since, remember f of x is the same as f of x squared. So really, my new function is f of x plus 2. And I want to give it a new name, so I call it h of x. So if you want to add a positive number to the parent function, it moves it up or down. Okay, pretty straightforward. Okay. Now the next thing is to do a vertical shift down, and you got it. If you want to move it down by 1 unit, you're going to subtract. So that's my 1, and you'll see what I do right here. I'm just going to take it, I'm going to take that 1 and subtract it. That's going to make bring all the y coordinates down. So when if you notice over here, look at the graph of f of x equal x squared, and notice how the y coordinate changed. The original one was 0, 1. And now when we move it down, we're pulling this point is what gets moved down. And so that pulls the old 0, the old intercept away, and we have a new one, 1, 0. So it's important to keep that stuff in mind. I'm going to actually go back to the slide before, because the same thing happens. I'm sorry, a different thing happens. Notice that we don't have, here's the original 0, and there's no zeros in the second one. So one of the things that you want to check about, I'm not going to make too big of a deal about it yet, but it's like you want to see what happens to the intercepts. Okay, so I want to summarize the vertical shifts. To go up, you add. To go down, you subtract. So when I add plus c, I go up, I'm increasing y, and then when I subtract c, I'm moving it down. Okay. Now the second kind of non-rigid shifts are going to be moving it right or left. And first I'm going to do it right. I want to move the graph to the right by 2 units. And as you see, that's what I did here. Let me take this off, and I want to go down here. And then I just want to point out that this original 0 here is 0, 0. And now my new 0, where I hit the x-intercept, that's going to be 2, 0. So notice I shifted the 0. I moved to the right. Okay, so then to move right, you subtract. So I'm going to just do this. See how you have the minus? I'm going to indicate I'm doing it right, moving it to the right. And that's because you need more x's. Now, if I wanted to get a 4 into this function, I just plugged in x equal 4. Now, if I want this function to equal 4, notice I have to plug in 6 to get 4. So I need more x's, and that's why subtracting shifts it to the right. So in general, subtracting a positive number inside the parent function, it moves it right. Okay, so we'll go to the next one. So I want to move it left, and yes, you're going to add. So when I add, I move things to the left. So again, I want to look at x plus 3. I'm going to take x cubed. I'm going to move it to the left. So inside the parentheses, I add 3 to it, and then I cube it. Here's the graph. So again, here's the old graph. And again, notice that what happens to the 0, it was 0, 0 here. And now the 0 is going to be at the point 3, 0. Okay. So again, a summary. If I want to move right, I subtract. So again, this subtracting moves it right. And then if I want to go left, I'm going to add. So addition moves it to the left. Okay. So here's an example where I'm going to do both. And so what I'm going to do is I'm going to take the graph of x cubed. I want to sketch this graph. And the way I'm going to sketch it is I'm going to say, oh, this is basically x cubed, but I'm shifting it. So this is going to be my horizontal shift right here. And then over here where the 1 is, this is going to be my vertical shift. So what I want you to do is pause, try to figure out, without using Desmos or anything, try to figure out what this graph g of x is going to look like. So you hit pause and work on it. I'm going to go to the next slide. Okay. So welcome back. Hopefully you figured this out. So again, we're going to take the way to look at this graph of g of x is to relate it, because of the cubing here, sorry, do that, is to relate this graph to the cubing function right here. Okay. So what do I do? Well, I'm going to look at the 1 first, and that moves it up by 1. And that's going to happen right here. That's going to be my up. I'm going to do that over here just so you can kind of see what's going on. Sorry, this is going to be hard to do in a nice way. There we go. Not too bad. Okay. Now notice, to move it up, what happens to the 0 is this point comes up here. So this point now is at 1. So again, my new 0 is going to be, it was 0, 0, and now it's minus 1, 0. So I've already shifted the 0 by 1. That's minus 1, 0 right there. 0, 0, of course, is just right here. So keep that in mind. Now I'm going to move. Now I'm going to do the shift left by 2. So remember, left is going to be adding. So that's what happens over here. I add 2, so I just shifted left by 2. And so now I'm going to do that. So I'm taking this graph and moving it over here. Notice that the new 0 is going to be there, 3, 0. Yep, that's exactly what happens. We're at minus 3, 0 right here. Okay. So just keep in mind that the zeros shift, and they shift in funny ways, so you want to keep track of it. So again, just a quick review. To graph this, we say, oh, this is a shift left by 2, and this is a shift up by 1. So I did that shift first. You'll get the same answer either way, but I just prefer to do this one first. Okay, so the difference between rigid and non-rigid shifts, we haven't seen the non-rigid yet, so I'm going to introduce them to you, is that when we do the rigid transformations, when we do either of these, we don't change the shape of the graph. The graph stays the same shape. Now when we do this, when we do a non-rigid transformation, we cause a distortion. there's going to be a change in the graph. So again, this is an example. These are examples of non-rigid. And we'll see what happens in the next couple of examples. So, for example, when I do a non-rigid transformation, again, if I look at the one that's going to be c times x, what we're going to see is it's going to be a horizontal shrink when c is greater than 1. That means it's almost like pushing the graph together and closer, and then it's going to be a horizontal stretch when c is between 0 and 1. That's going to be like pulling the graph out horizontally. And we see something similar happens here when we look at the graph that's c times f of x. In other words, we taking the function and multiplying it times c. We're going to get a vertical stretch. We're going to pull it up when c is by 1, and a vertical shrink. We're going to pull it down kind of when c is between 1. So we'll see these in some examples, and we'll come back to these. Okay. So I'm going to take the absolute value parent function right here, and then I want to look at y equal 3 of x, which is 3 absolute x. And I'm going to, again, call that h of x since it's a new function. So that's my absolute value. So I want you to pause, try to work this out, and then join me on the next slide. And again, I used a table of values, so I'll let you think about how you want to do it. So I'm going to go to the next slide. I'll see you on the other side. Okay, so welcome back. I want to compare the parent graph, of this function to, to the graph 3 absolute x. Okay, and rather than think too hard about it, I made a table of values. I know what the absolute value shape look like, so I can plot these points and I can just connect the graph. So in other words, for h of x, if I plug in x equal 1, for absolute x, if I plug in 1, I get 1. For 3 times f of x, I'm going to get 3 at that point. So here I'm going to have this point's going to be up here somewhere. That's going to be the point 1, 3 on the new graph. And you can see it's going to be inside. So in other words, it's almost like I'm taking this graph and moving it up. Then I plug in minus 1, and I'm going to get 3 over here, so I'm going to get this point on the new graph. And then I'll start sketching the graph just a little bit. You can see the graph is going to go like that. And by stretching, what I kind of mean is I'm pulling this. I'm stretching this in that direction. And I'm stretching this way. So it's almost like I'm pulling this that direction. That's what I mean by stretching. I'm pulling it up. And so here you have the graphs. You see the new graph is inside the old graph, the graph of 3 absolute x. And that's what it means by a stretch. Again, I imagine that I just imagine pulling this way. I'm pulling it up. That's a stretch to me. And that's what that's kind of what they mean by a stretch. And just to go back and look to see what happened, we were in this case right here. C was equal to 3. It says when C is greater than 1, it's a vertical stretch. That's exactly what happened. Okay. Now, I want to compare the parent graph to what happens when I multiply by 0.05 or 1/2 and then to x and then apply the function. So I'm going to be looking at this function, and I want you to try to think about what the graph of this function looks like right here. Pause, do some work, and then join me in the next slide. Okay. So here I am at the next slide, and again I did a table of values, and I'm going to multiply 1/2 by x before taking the absolute value. So I do that over here, and obviously if I take 1 times 1/2, I'm going to get 1/2 inside the absolute value, which gives me 1/2. If I take minus 1 times 1/2, I get minus 0.5, but the absolute value makes it positive. So I get 0.5, and notice that I have the graph 1. This is going to be where those new points are. That's going to be 1.5. And then over here in the new one, I get minus 1.5. I'm writing this 1/2. And then I use the table and I get a couple of other points. I get the point minus 2, 1, which is right here. And then I'm looking at this point over here. When I plug in x equal 2, I get 1. So I get this point over here. And you can see that this graph has been stretched. It's like I pulled it this way to stretch it out. I've stretched this out in the vertical direction. I'm sorry, in the horizontal direction. Okay. Okay. So those are some examples. I'm going to go back, actually. What I'm interested in you doing is I'd like you to understand what the concept is. We would. But at the same time, you want to be practical. You want to be able to graph them kind of by whatever means necessary. But you want to understand what you see. That's what I'm hoping you do, is that from this will help you understand a little bit about what you see. Okay. So there's two special transformations. And one of them is we don't change the shape of the graph for either. But one of them is when we just take the function and multiply by minus 1. We don't change the size, but the graph gets flipped over or reflected over the x-axis. And the reason is what was negative is multiplied by minus 1. That's now positive, and vice versa. What was once positive, when you multiply it, gets negative. So when you have something that was on one side of the x-axis, it gets flipped to the other side. And we'll go through with an example about this. And then if c is minus 1, and you want to look at the difference between this and f of x, again, since we're multiplying by 1 or minus 1, we're not changing the size or the shape, but we're flipping it over the y-axis. Because what was on the right of the y-axis is now on the left of that. Because when you make an x negative, if you have 3 and you make it negative, this was on the right side, and now it's on the left side of the x-axis. So x equals 3 is on the right side of 0, and that's going to be on the 0. So it flips things around. So we'll go through some examples of this. Okay, I want you to compare the graphs of f of x equals x squared, and then minus f equals minus x squared. Pause, think about it, try to graph it. Try to do it, use thinking about it, but if you need to, look at a graph, look at Desmos or something, and then try to understand what you see. So while you pause and work out it, I'm going to the next slide. Okay, so here, just want to show you a couple of things. Let's say this is the point up here. It's not quite, but let's pretend this was the point 2, 4. Because we multiply, that 4 gets multiplied by minus 1. This is now the point down here, and it's still x equals 2, but we get minus 4 because we've multiplied 4 times minus 1. Again, another thing, we had the point 1, 1. Since y is greater than 1, it was on the upside of the x-axis. Now we look at it, we multiply 1 by minus 1, and we get, sorry, this is minus 1, 1. Now we get minus 1, 1, so this point is now right down here. So again, when we multiply our y-coordinate by minus 1, it flips it across the x-axis. Remember, flips is the same as reflects. Okay, so now on to the next one. I want to compare the graphs of, again, the parent function, f of x equal x squared, and what we get when we look at minus x squared. So again, we're going to take minus x and then square it. Now notice what happens when I square this. I get x squared. That's all I'm going to say. I'll let you pause, think about it, and think about what this graph, how it's going to compare to this graph right here. Okay, so pause, think about it. I'm going to advance, and I'll see you there. Okay, so if you noticed that since this graph, minus x quantity squared is the same as x squared, h of x, even though it looked different, is the same as f of x. So in this particular case, the graphs are the same. They don't change. And again, I'm just trying to say this right here, that for an example, f of minus 3 is 9, and then h of 3, which is going to be h of, remember, f of minus 3 is equal to h of minus 3. You get the same y value, so nothing's changed. We have the same pairs of the graph. Again, the best way to see that is that these two functions are the same. Okay, I don't want to say too much more about that. Here's another example. I want you to compare the graphs of x cubed, f of x equal x cubed, and then f of minus x, which is minus x cubed. So we get that. Okay, so again, we want to change these two when we compare these two graphs. Okay, so sorry. Here. Why don't you go back, pause, work on it, and join me there. Okay, let's pretend I didn't jump ahead, okay, and give you a sneak preview. Okay, so now we'll go ahead. Okay, so if you notice, here's the original graph in red, and here's the new graph in black. And notice that it flipped everything across the x-axis. So that went over here, and this part went over here. Now notice with y equal x squared, oops. So I'm looking at the other example. I think it's good to compare. And then we had f of minus x equal x squared. When I flip across the axis, I get the same thing because these were already symmetric to the y-axis. So remember, I had the point 2, 4 on, and if I flip that across, I get minus 2, 4. That's already there. So here, there's nothing there, so when I move this across, you can see how I get that. Okay, I think that's going to be enough for this. I want to summarize things right now. I'm going to skip the next slide. I had something there, but actually I really don't want to look at that right now. I think we've had enough. So this is just summary. To shift a graph up by c units, you add positive c. To shift it down by c units, you subtract c. So that's down. This is up. Now to shift a graph right, you subtract. And you change f of x to f of x minus c. To shift left by c, you add. And then you get f of x plus c. So that's going to be, this is going to be the right shift, and this is going to be the left shift. Okay. So special rigid shifts are going to be reflections. And again, if we look at y equal minus f of x, that flips across the x-axis. And then if we change y equal f of x to y equal minus x, that flips and reflects the graph over the y-axis. Now notice if the function is even, and remember in an even function, f of x equals f of minus x, that doesn't change the function. Okay, that's just sort of an extra thing. You don't need to worry about that. Now these shifts are rigid because the shape of the graph doesn't change, only its position. And again, I want to do, when I change the name to g of x or h of x sometimes, I think I use both. What I'm trying to say here is I change the parent function. Okay, so here's the non-rigid shifts, and this just summarizes that if I multiply c times x, that shrinks horizontally. If I multiply c times f of x, that's going to shrink vertically. These are the examples I did earlier. if we multiply c of x times c less than 1, I stretch vertically. And if I multiply it by c greater than 1, the entire function, I'm going to stretch vertically. So again, these are just good things to keep track of. Okay, well, that's it for today. Thank you. Bye-bye.